Alright, so let's talk about the third case. So we had our roots negative lambda plus or minus square root of lambda square minus w square. So if lambda square minus w square is negative, you get complex roots. Okay, so let's use simple notation. Let's say we got our roots to be alpha plus or minus beta I. That is the standard notation that we used, right? So what is the solution look like? So x is c1 e to the alpha t, remember cosine beta t plus sine beta t. Again, you have to do this transition from independent variable from x to t. So get used to that, okay? So here x is our dependent variable. Now, this is how a solution will look like when you have complex roots for a free damped motion. Now, my question for you is, what do you expect from the behavior of the motion? So previous motions, over damped motions and critically damped motion, the solutions were all only exponential functions, exponential decay. So in the motion, you didn't have oscillatory behavior, because oscillatory behavior is coming from what? Sine cosine functions, right? Like sine curves, cosine curves. But here, when you have complex roots, you do have these sine cosine functions in the solution. So can you able to see oscillatory behavior when you have complex roots? Of course, yes. You will be able to see a very oscillatory motion. But again, in the physical sense, what should happen to the motion? Well, motion should go to 0, right? Because this is a still damped system, right? So when you have a damping, okay, when you have damping, what happens is the energy drains away. So ideally, you have both oscillation behavior in this solution plus the exponential decay. So you will be able to see both. Okay, let's see an example. All right. And then let's see an example. Yes, we'll start from an example. So a mass of 0.5 slugs. So here the units are very important. So slug is actually pounds second square over feet. Okay, so let's make sure we are on the same page. Is suspended with spring constant K, which is 4 lb over feet. Now W square is K over M. Now K is 4, M is 0.5, but does the units match? Because W square should have 1 over second square units, right? So you have to be careful. So 4 is actually pounds over feet and 0.5 is slug. So 1 over slug means you have to take the reciprocal of this. So feet over lb second square. So lb cancel out, feet cancel out. So in fact, W square is still 1 over second square when we use slug. So 4 over 0.5 is actually 8. So W square is 8. And then the question says an interesting thing. The damping force numerically equal to 2 times the instantaneous velocity. So actually what that means is 2 lambda times dx over dt is the instantaneous velocity. So it's actually, this is the damping force, okay? So it's actually 2 times the velocity. That is what it means. Or that 2 here means 2 lambda is 2. Okay, that is another way to put it. So your differential equation is 2 lambda is 2 dx over dt, W square is 8, so plus 8x equal to 0. So that is the differential equation. Now then we have to look at the initial condition. The mass is pulled down, so x0 is pulled down 1 foot, okay, and released. So it only says released. So release means what is the initial, only says released. Okay, that's the difference. In previous problems we said release with a certain speed. So here release means it's released from initial 0 speed. Okay, just a released. Okay, all right. So those are the initial conditions. So let's solve it. Again, we need the auxiliary equation. m square plus 2m plus 8 is equal to 0. So let's use the quadratic formula. So negative 2 plus or minus 2 square is 4 minus 4 times 8 is 4 times 8 is 32 over divide by 2a is 2. So negative 2 plus or minus 4 minus 32 is negative 28. So square root of negative 28 over 2, which means, let's write here. So the roots are negative 2 plus or minus 28 is 7 times 4. So the square root of 7 times 4 is, we can take the square root of 4. So it's 2 square root of 7 I, right? Square root of negative 1 is I. So divide by 2. So if we divide each term by 2, negative 1 plus or minus square root of 7I. 2 cancel out. So alpha is negative 1, beta is square root 7. Okay, so that is what we need to write down the solution. So the solution is e to the alpha is negative 1. So e to the negative t. C1 cosine beta is not 2, square root 7t plus C2 sine beta square root 7t. So this is the solution. Now you can see in the solution you have both oscillations and exponential decay. But what do you think will happen eventually? Well, exponential decay, when we say, so when limit time goes to infinity, exponential decay means very fast you approach to 0. So comparing to cosine and sine terms, exponential term is very powerful. Exponential decay is very powerful. So what happens is exponential decay term will dominate over sine and cosine. So even though you have oscillatory motion, it will damped out to 0. So the motion will still approach to the rest position even though you have oscillations. But the difference from overdamped and critically damped situations, here you have oscillations in the motion but you still approach to rest position. This behavior we say underdamped motion. Okay, so we have complex roots and damping is a little bit small comparing to the spring constant. So but still you approach to the rest position, but you have oscillations present because you have complex roots. So this is the graphical explanation of the graphs. You can see there are some oscillations here, right? See, you have sine wave, sine, cosine waves sort of behavior, but you can see it still approaches to 0 very fast because exponential decay dominates. Okay, so I encourage you to use these initial conditions and get the solution finding C1 and C2. I'm not going to do that here. Okay, I will leave it as an exercise. Now let's summarize. So we have three cases: overdamped, critically damped, underdamped. Okay, so this should have been underdamped. So overdamped, you get the overdamped case when you have two distinct real negative roots. Roots will be negative, exponential decay behavior, no oscillations in your solution. You will have exponential functions and you will approach to the rest position. Critically damped, well, is same behavior, but you have repeated roots. Still you approach to the rest position, right? But when you have complex roots, you have both oscillations and exponential decay. Still the damping is there, but again you approach to the rest position eventually. Okay, so that is the most common thing between these three motions. No matter what you have, you approach to the rest position. The displacement will be 0 eventually. And in a free damp motion, the solution is always a transient term. It depends on the time, all the time. Okay, all these three type of solutions. Okay, so we call them a transient solution. The complementary solution is a transient solution. Okay, so that's the summary of what happens when you have damping plus no external force or no driving force. So we say free undamped motion. Okay, so in the next couple of videos, what we are going to learn is what happens when you have driving force when the differential equation is non-homogeneous. Okay, we'll see you in the next video. Thank you.